Continuing in section 5.4, let's look at proving a couple of identities here. So just like we did in section 5.2, when you were looking to prove that one side was equal to the other, you'll be doing the same thing here. Keep in mind, again, that they ask us to prove some things, and they usually aren't trying to trick us to say, no, this isn't true. So when they ask you to prove in this section, assume that the identities you're looking at are true, and we just have to figure out how we're going to show that they are true. So when I look at the cosine to the fourth minus the sine of fourth of x, that equals cosine of 2x. We saw something like this on our previous worksheet where we had something to the fourth. So just a reminder of how that factoring is going to work. We know that that factors as x squared minus y squared times x squared plus y squared. That would be a difference of squares, right? So the x to the fourth minus y to the fourth is still a difference of squares. So that's what we're going to use on this left-hand side. I have the cosine to the fourth minus sine to the fourth. I always like to start with the side that start by writing down the side that I am starting the process with. And so when I factor this, that's going to give me cosine squared minus sine squared times cosine squared plus sine squared. Ah, look at that, cosine squared plus sine squared, magic. That's equal to 1 right there. And so if that's times 1, what does that leave us with? That leaves me with cosine squared minus the sine squared. And lo and behold, this is your identity from the first sheet of your notes here. So cosine squared minus sine squared is equal to the cosine of 2x, which is exactly what you were trying to prove. In example number 3, we're going to look to prove that the sine of 8u is equal to 2 times the sine of 4u times the cosine of 4u. Now this looks kind of like just a double angle identity for the sine. If we think about that the sine of 2 times x, the identity said that that was 2 times the sine of x times the cosine of x. So it kind of seems like it's really just straight a double angle identity itself. We have double of a number right here, right? That's the 2x part. And then in the end, this is 2 times the sine and the cosine of just the regular x, half of that starting point. So check out how this looks. The sine of 8u, 8 right here, is 2 times half of that angle, the 4 that we have there. So it seems like it fits directly with the double angle. Now how we're going to prove that is we're going to start with the sine of 8u, and we're going to use the sum and difference identity. How would you know? I guess because I told you. You probably wouldn't think about it all on your own the first time, but now when you see one like this in the homework, you will recognize that you'll want to split that up using a sum and difference identity. So the sine of 4u plus 4u, using those identities that you talked about yesterday in section 5.3, I can rewrite that function. And so those identities, that tells me it's the sine of 4u times the cosine of 4u plus the cosine of 4u times the sine of 4u. Sine times cosine, cosine times sine, that's the same thing. So that means I have 2 of the sine times cosine. And that's exactly what we're looking for to prove there. All right, and the last thing for us to look at in this section would be the half angle identities. When they're saying that we're using a half angle identity, it means that the angle they gave me is exactly half of some nice number. Now this only works then in a very limited number of cases for something to be exactly half of a nice number, which by nice number we mean something that has a nice reference angle. So maybe it's a 30-degree angle, or maybe it's something that has a 30-degree reference angle like 150 or 210 or something like that. So this is the identity, and again, you don't have to memorize it, we just have to know how to use it. And the big thing to point out here is that you're going to see a plus or minus in front of all of these formulas here. The plus or minus, you're not going to write that every time. It's not like when I say x squared equals 36, and now I tell you x equals plus or minus 6. It is not the same as that. This plus or minus is just to tell us it could be positive or it could be negative. So that's the big note that you have here. The sign in front of the radical depends on the quadrant. You need to decide this. So we're going to look at the angles they give us, and we're going to decide, hey, is my answer positive or is it negative? But it's not going to be both, and we have to come up with that. So let's take a look at a couple examples about that. First one, find the exact value of the cosine of 5 pi over 8. If they give it to us in radians, that's fine. Oftentimes you're going to want to switch that to degrees just because we're more comfortable working with that to start. So I might rewrite this 5 pi over 8. You're going to figure that out in degrees. Pi is 180, so 5 times 180 over 8 is going to give me the cosine of 112.5 degrees. Whoa, 112.5 degrees. Definitely does not have a nice reference angle with that 0.5 in there. However, when we think about that, what I know is that if that's the cosine of 112.5, double that. Double that. Now, sometimes that's weird for people because they say this is the half angle. Why am I doubling it? Remember, that means this is half of some nice angle. So if I double this, I find out that this is the same as 225 degrees divided by 2. Ah, look at that. So our original angle in red is exactly half of 225 degrees, which does have a nice reference angle. Let's sketch it over on the side because we're going to use that a little bit later anyway. The 225 degrees right about here, and that has a nice 45-degree reference angle. All right, so now we know what this is going to look like. Remember, it's the cosine of x over 2, so our x value is 225 divided by 2. That brings us back to our original red value, and x is what then gets substituted inside that square root. Now, before we go too far, just so that we don't forget about it, remember that the plus or minus depends on the quadrant. And so let's think about what we have. We have the cosine as our trig function, and our actual angle. Don't use the other angle once you found the x. Think about the actual angle that they told us. This is 112.5 degrees. That means that we're in the second quadrant. Cosine in the second quadrant is negative. So I'm just going to make a little note for myself over here. Quadrant 2, therefore, this final answer is going to be negative. So just a little reminder to myself somewhere off to the side to make sure I put that negative sign in as I'm solving. All right, so now let's plug it into the formula. The plugging in isn't so bad. It's the algebra to simplify that we have to watch out for. So we just decided, I'm going to switch colors here again. We just decided that we are going to want a negative out in front of that square root symbol because of the quadrant that we're in. And then we have 1 plus the cosine of x. Remember, x being the value on the top of the fraction, which is going to be that 225. So we have 1 plus the cosine of 225 degrees, all divided by 2. All right, so that's the plugging in part. Now let's start simplifying. The cosine of 225, what's that equal to? Well, when we have our reference angle here, that was the 45, 90. You've got 1 square root of 2. Now this went down 1, this went to the left 1, so it looks like the cosine of 225 degrees, when I use that reference angle, cosine being adjacent over hypotenuse, you've got -1 over square root of 2. Remember that in general, we want to write those as the square root of 2 over 2, and that's going to help our simplifying as well. So this is equivalent, but generally we want to try to rationalize that to be the square root of 2 over 2. So I'm going to substitute that for the cosine. So my next step is going to look like still keeping that negative out front. Now I have 1 plus negative square root of 2 over 2, and the whole thing is still divided by 2. All right, keep on going with our algebra because we've got a couple things that we don't like. We don't like a fraction within a fraction. Also, remember the square root, everything's under the square root. I guess that gray line didn't go down all that far, but even this 2 in the denominator is underneath the square root as well. And so we want to get rid of those things too. How do we do that? To get rid of the fraction within a fraction, we had talked about earlier in the year, multiplying by the common denominator that you're trying to get rid of. So I'm going to multiply by a 2 over 2. Again, I'm picking that because the 2 is in the denominator. As a little side note off to the right, I'll erase it here in just a second. I think we did a couple examples where we said, what if I had 1/3 plus 1/6 over 1/4 plus 1/12, and I had to add those all together. And we talked about that if we multiply by what that common denominator would be, in this case that would be 12, if I multiply by that common denominator, it gets rid of all of my fractions quickly, right? Distribute that 12 through, gives you 4 plus 2 over 3 plus 1. Very quickly, I went from something that looks kind of messy and that a lot of people don't want to do just in their head to something that I can very quickly evaluate. So that's what we're trying to do here when we multiply by a 2 over 2. Just to give myself some more space because I'm going to need that over here. All right, so if I keep on simplifying, I'm going to distribute that 2 through. Again, keeping my negative in front of that square root. When I distribute the 2, I get a 2 on the top. I get a minus square root of 2, right? This 2 on the bottom will cancel out with the 2 out front. So 2 minus square root of 2, all divided by 4. And then the last step that I have, remember that when it's the square root on the top and the bottom, I can evaluate each of those things individually. So the denominator, the square root of 4, really is just a 2. So I'm going to get rid of that square root. That leaves me with the negative square root of 2 minus square root of 2. All right, we will use the same solving strategy to get to letter B for the sine of 5 pi over 12. And so again, the first thing you want to do is figure out what's that angle in degrees. So we get the sine of 75 degrees. Now 75, remember, is in quadrant number 1, thinking of my original angle. So that means if we're in quadrant number 1, I'm only going to be dealing with the positive part of this answer. So with my plus or minus, I only need to deal with the positive. And then remember, we said, well, what's double of this? Because we're saying this is half of some nice number. Double of that gives me 150 degrees over 2. All right, so again, I would say, why don't you pause this video, take a minute to simplify this, and see if your answer matches up with mine. All right, so looking at our final answer, we get the square root of 2 plus the square root of 3, all divided by 2 for our final answer. Again, noticing that that was positive, so in my first step here, I just wrote a positive to reiterate that it's not both the plus and the minus. It's just the positive part of that answer. And then we multiply by 2 to get rid of those fractions. The square root of 4 was equal to 2, and that leads us to our final answer. Now, one question I get pretty often is, wait, couldn't I have used the sum and difference identity with this? And of course you could have, right? The sine of 75, our original number, definitely could have been written as the sine of 30 plus 45. Now, if you did a sum and difference identity, the answer looks a little bit different, but it's the same decimal value. It's equivalent value to one another. It just looks a little bit different in its exact form, but it definitely would be possible to do that. And that's why oftentimes when you see the sum and difference and the half angle identities, they will specifically say use a half angle identity or use a sum and difference identity to verify. And that's what I'll be looking for on your quizzes as well, will be to figure out what exact identity do you want to use so that I'm evaluating you on the right process there. So just keep that in mind for your final answers there. On the bottom of your note sheet, you do see a couple alternate forms for our tangent identity that you might end up using. And just like we said before, the sine over the cosine can also always be used as a formula for the tangent.